Above the atmosphere, beyond the reach of clouds and weather, another kind of precipitation takes place. Every second of every day, thousands upon thousands of microscopic particles drift down through the vacuum of space, each one no larger than a grain of pollen, each one carrying within its crystalline structure the chemical signature of worlds beyond Earth. They arrive without fanfare, without the dramatic streak of shooting stars, settling instead with the patient inevitability of geological time itself. These cosmic visitors have been falling for 4.5 billion years, a steady accumulation that began when Earth was still molten and continues now as satellites orbit overhead and cities glow beneath the stars. Scientists estimate that between 15 and 300 tons of this extraterrestrial material settles onto our planet each day. The uncertainty itself a reminder of how much mystery still surrounds this ancient process. The particles arrive as silently as snowflakes, each one a messenger from the outer reaches of the solar system. The very air carries their presence. High in the stratosphere, specialized aircraft equipped with aerogel collectors sweep through the thin atmosphere, gathering these visitors before they can be contaminated by earthly elements. The collection plates return filled with particles so small they exist at the boundary between matter and emptiness, specks that formed in the stellar nurseries of distant galaxies, travelled for eons through interstellar space, and finally found their way to our small corner of the cosmic dance. Some of these particles formed in the cooling gas around dying stars, condensing from stellar winds that carried the nuclear ashes of supernovae across light years of emptiness. Others crystallized in the outer reaches of our own solar system, where temperatures hover just above absolute zero, and sunlight arrives as barely more than starlight. A few bear the chemical signatures of processes that occurred before the sun ignited, relics from the molecular cloud that collapsed to form our entire solar system. In laboratory clean rooms around the world, researchers examine these microscopic travelers under electron microscopes, revealing structures more delicate than butterfly wings, yet tough enough to survive journeys spanning millions of kilometers and millions of years. Some particles show the glassy sheen of rapid cooling in the vacuum of space. Others display the layered architecture of slow crystallization in the frigid darkness between worlds. A few bear the scars of cosmic ray bombardment, their surfaces pitted by high-energy particles streaming from distant stars. The examination process itself requires extraordinary patience. Each particle must be extracted from its collector using techniques borrowed from microsurgery, manipulated with tools so fine they can move individual atoms under the electron microscope's beam. These cosmic grains reveal their secrets, mineral structures unknown on Earth, isotopic ratios that tell stories of stellar evolution, organic compounds that formed in the interstellar medium billions of years before life emerged from Earth's primordial oceans. The irony rests in plain sight. While humans have spent centuries dreaming of touching the stars have been touching us all along, settling quietly into ocean sediments and polar ice, accumulating in the corners of gutters and on the surfaces of leaves. Every breath contains atoms that once drifted free in the cosmic wind. Every handful of soil holds fragments of asteroids that formed when the solar system was young. The dust that settles on windowsills contains, in microscopic quantities, the substance of comets and the debris of worlds that never quite became planets. These particles carry within them isotopic ratios unknown on Earth, signatures of nuclear processes that occurred in stellar cores billions of years ago, markers of chemical reactions that took place in the outer reaches of the solar nebula before planets had names or observers to name them. Each microscopic grain represents a data point in the vast experiment of cosmic evolution, a single verse in the longer poem of Matter and Time. The scientific instruments designed to study these visitors push against the limits of measurement itself. Mass spectrometers sensitive enough to detect individual atoms pass the chemical composition of grains smaller than bacteria. X-ray diffraction patterns reveal crystal structures that formed under conditions impossible to recreate in terrestrial laboratories. Scanning electron microscopes map surface features measured in nanometers, creating portraits of textures sculpted by radiation pressure and solar wind over geological ages. Yet, for all the sophisticated analysis, perhaps the most remarkable aspect of this cosmic precipitation lies in its quiet persistence. Right now, as you listen to these words, particles that began their journey when dinosaurs ruled the Earth are settling onto the planet's surface. Others that started their descent during the last ice age are still drifting through the outer atmosphere, their arrival delayed by atmospheric dynamics and electromagnetic fields. The particles themselves seem almost impossibly small to carry such profound implications. A typical interplanetary dust grain measures between 1 and 100 micrometers across, dimensions that place them in the realm of bacteria and pollen, invisible to the naked eye, yet massive enough to carry within their structure the memory of cosmic processes spanning billions of years. They exist at the intersection of the infinitesimal and the infinite, bridges between the human scale of experience and the vast scales of space and time. Tonight, as darkness spreads across continents and stars emerge in the deepening sky, approximately 40,000 of these cosmic visitors will settle onto each square kilometre of Earth's surface. They fall onto mountains and cities, forests and deserts, adding their infinitesimal weight to a planet that has been growing heavier, grain by grain, since the beginning. Only took 4 billion years to build a library written in dust, and the writing continues still, letter by microscopic letter, in a language older than life itself. The collection continues in perfect silence, a cosmic punctuation that marks the passage of deep time with the gentle accumulation of stardust on stone. Each particle a period at the end of a sentence written in the motion of worlds around distant suns. Each grain a reminder that the universe is not empty space punctuated by occasional matter, but rather a continuous fabric of connection spanning the distance between atoms and galaxies. In the hours before dawn, when darkness reaches its deepest point and city lights dim to their lowest glow, a faint luminescence begins to emerge along the eastern horizon. This is not the first blush of sunrise, but something far more ancient and mysterious, a ghostly pyramid of light that stretches upward from the horizon. Following the path the sun will trace across the sky hours later, astronomers call this phenomenon the zodiacal light, and for centuries it remained one of the most beautiful mysteries visible to the naked eye. The light appears so delicate that even the smallest amount of atmospheric haze or light pollution can erase it completely from view. In desert locations far from cities, where the air carries no moisture and no artificial illumination drowns the subtle glow, the zodiacal light reveals itself as a pale, tapering cone that can extend halfway to the zenith. Ancient Persian astronomers called it the false dawn, mistaking its gentle radiance for the approaching sunrise. Medieval Islamic scholars documented its appearance with careful precision, noting how it shifted position with the seasons and varied in brightness throughout the year. What these early observers could not have known is that they were witnessing sunlight scattered by a vast disk of debris that extends throughout the inner solar system, the same cosmic dust that settles continuously onto Earth's surface. This interplanetary medium represents the accumulated detritus of billions of years of solar system evolution. A slowly rotating carousel of particles that follows the same general plane as the planets themselves. The zodiacal light is nothing more than sunlight reflecting off countless microscopic grains, each one too small to see individually, but collectively numerous enough to paint the pre-dawn sky with their scattered radiance. The disk itself extends from well inside Mercury's orbit all the way beyond Mars, with the greatest concentration of particles lying in the asteroid belt and the inner regions where Earth orbits. Scientists estimate that this debris field contains somewhere between 10 to the 13th and 10 to the 19th kilograms of material, a mass equivalent to a small asteroid distributed across billions of cubic kilometers of space. The precise number remains uncertain because the particles exist at densities so low they challenge the fundamental definition of matter itself. Each particle in this vast collection has its own story of origin and wandering. Some formed in the outer reaches of the solar system, where comets shed their substance as they approach the sun's warmth. Others represent the ground-down remains of asteroid collisions, fragments of fragments that have been pulverized and repulverized over geological time until they exist as little more than organized clouds of silicon and iron. A few carry within their crystal matrices the chemical signatures of interstellar space, visitors from other solar systems that have been captured by our sun's gravitational influence. The zodiacal light varies in intensity throughout the year, growing brighter during certain seasons as Earth's orbit carries it through denser regions of the debris field. In the autumn months, when the ecliptic plane makes its steepest angle with the western horizon after sunset, the glow can become prominent enough to cast faint shadows in locations with perfectly dark skies. Spring brings the most spectacular displays of the morning zodiacal light, when the pre-dawn hours reveal the full extent of the cosmic dust clouds stretching along the path of the planets. Modern space missions have sailed directly through this debris field, their instruments recording the constant patter of microscopic impacts against their hulls and solar panels. The Pioneer and Voyager spacecraft, during their journeys to the outer planets, documented the gradual decrease in particle density as they travelled beyond Mars. Their dust detectors registered impacts from grains so small that individual collisions released energy measured in fractions of a joule, yet so numerous that the cumulative bombardment slowly eroded the spacecraft's surfaces over years of interplanetary travel. The Ulysses mission, launched to study the Sun's polar regions, provided the first comprehensive map of dust density throughout the inner solar system. Its instruments revealed that the debris field is not uniform but contains streams and clusters that correspond to the orbital paths of defunct comets. These gravitational sculptures in dust mark the passage of ancient visitors that have long since exhausted their volatile materials, leaving behind only the rocky skeletons of their passage preserved in patterns of drifting particles. What strikes researchers as particularly remarkable is the dynamic nature of this seemingly static phenomenon. The zodiacal light appears constant from Earth's perspective, a reliable feature that photographers can plan their expeditions around. Yet the individual particles creating the glow are in constant motion. Computer simulations reveal that a typical dust grain in the inner solar system follows a complex trajectory influenced by solar radiation pressure, gravitational perturbations from the planets, and electromagnetic forces generated by the Sun's magnetic field. The Poynting-Robertson effect, first described in the early 20th century, ensures that these particles cannot maintain stable orbits indefinitely. Sunlight carries momentum, and when photons strike a dust grain and are absorbed or re-radiated, they impart a tiny but persistent force that gradually slows the particle's orbital motion. Over timescales measured in thousands to millions of years, this cosmic friction causes particles to spiral slowly inward toward the Sun, where they are eventually vaporized in the solar atmosphere. This process of orbital decay means that the zodiacal cloud requires constant replenishment to maintain its observed density. The source of this renewal represents one of the ongoing puzzles in planetary science. Comets contribute material each time they pass through the inner solar system, shedding dust and gas that eventually settles into the general debris field. Asteroid collisions generate fresh clouds of fragments that gradually disperse along orbital paths. Even the Moon contributes microscopic ejecta when meteoroids strike its airless surface, launching plumes of lunar material into interplanetary space. Recent observations from the Spitzer Space Telescope and other infrared observatories have revealed additional structure within the zodiacal cloud that was invisible to earlier ground-based studies. These instruments detect thermal emission from dust grains warmed by sunlight, creating maps of particle density that show features resembling spiral arms and ring structures. Some of these patterns appear to correlate with the orbital resonances of Jupiter and other giant planets, suggesting that gravitational influences shape the distribution of debris in ways that are still being understood. The very faintness of the zodiacal light serves as a reminder of how empty space actually is between the planets. Despite containing trillions upon trillions of particles, the interplanetary medium maintains a density so low that a spacecraft can travel for months without encountering a single grain large enough to damage its instruments. The light we see represents the collective reflection from a vast number of objects, each smaller than the width of a human hair, distributed across a volume that could contain thousands of Earths. Tonight, as the zodiacal light begins its slow emergence above the eastern horizon, it illuminates a debris field that has been accumulating for nearly as long as the solar system has existed. The gentle glow marks the presence of cosmic archaeology written in dust, a museum of solar system history that drifts through space in microscopic fragments. Each grain an artifact from the era when planets were still forming and the architecture of the solar system remained unfinished. Only took 5 billion years to build a monument made of emptiness and starlight, and still the ancient light continues to rise, revealing the presence of absence, the substance of space itself made visible through the patient accumulation of cosmic dust across the immeasurable distances between worlds. The individual particles that create the zodiacal light exist at a scale that challenges human comprehension, occupying the liminal space between the visible and the invisible, between matter and void. A typical interplanetary dust grain measures between 1 and 100 micrometers in diameter, dimensions that place these cosmic travelers in the same size range as bacteria, pollen grains, and the finest particles of clay. To appreciate their true scale, imagine a grain of table salt reduced to the size of a period on this page, then reduced again by the same proportion. Even then, the comparison fails to capture the extraordinary delicacy of these structures, which have survived journeys measured not in kilometers, but in astronomical units, not in days, but in geological epochs. Each particle represents a marvel of cosmic engineering, a microscopic spacecraft designed by the physics of space itself to survive conditions that would instantly destroy any human-made object. The vacuum of interplanetary space subjects these grains to temperature variations that swing from hundreds of degrees above absolute zero when illuminated by direct sunlight to the bitter cold of deep space when they pass into shadow. Cosmic radiation bathes them in high-energy particles that can alter their atomic structure at the most fundamental level. Solar wind, the constant stream of charged particles flowing outward from the sun, bombards their surfaces with ions traveling at velocities measured in hundreds of kilometers per second. Yet somehow, these microscopic structures endure. Scanning electron microscope images reveal surfaces sculpted by eons of cosmic weathering, displaying textures that range from smooth glassy coatings to intricate crystalline architectures. Some particles show evidence of multiple thermal cycles, their surfaces bearing the scars of repeated heating and cooling as their orbits carried them closer to and farther from the Sun. Others display the characteristic pitting caused by micrometeorite bombardment, their surfaces cratered by impacts from particles even smaller than themselves. The journey that brings these grains to Earth begins at distances that strain the imagination. Some particles originate in the Kuiper Belt, that vast ring of icy bodies that extends from Neptune's orbit to nearly twice that distance from the Sun. Others emerge from the even more distant Oort cloud, a spherical shell of cometary nuclei that marks the outermost boundary of the Sun's gravitational influence. From these remote regions, the particles begin their long migration inward, carried by gravitational perturbations, solar radiation pressure, and the complex dynamics of orbital mechanics. The timescales involved in this cosmic migration make human history seem like a brief flicker. Computer models suggest that a particle originating in the outer solar system might require anywhere from hundreds of thousands to tens of millions of years to spiral inward to Earth's vicinity. During this immense journey, the grain experiences billions of thermal cycles as its elliptical orbit carries it alternately closer to and farther from the Sun. It encounters gravitational influences from all the major planets, each encounter subtly altering its trajectory in ways that accumulate over time into significant changes in orbital characteristics. Throughout this journey, the particle slowly loses mass. The process begins with the sublimation of volatile materials, water ice, frozen carbon dioxide, and other compounds that vaporize when exposed to solar radiation. Gradually, only the most refractory materials remain: silicates, metals, and carbon-rich compounds that can withstand the harsh environment of interplanetary space. By the time a particle reaches the inner solar system, it has been refined by the cosmic furnace into a concentrate of the most durable substances in the universe. The physics governing these microscopic wanderers reveals phenomena that operate on scales both smaller and larger than everyday experience. Individual particles respond to forces that would be negligible for larger objects but become dominant at micrometer dimensions. The pressure exerted by sunlight, for instance, becomes a significant factor in determining orbital evolution when applied to surfaces with such high area-to-mass ratios. A dust grain experiences solar radiation pressure as a constant gentle push that gradually modifies its orbit over geological time. Electromagnetic forces also play crucial roles in the dynamics of interplanetary dust. Many particles acquire electric charges through interaction with the solar wind and cosmic radiation. These charged grains then respond to the Sun's magnetic field and the complex electromagnetic environment of interplanetary space. In some regions, particularly near planetary magnetospheres, electromagnetic forces can become more important than gravity in determining particle trajectories. The journey inward transforms each grain in subtle but measurable ways. Laboratory analysis of collected particles reveals evidence of space weathering, processes that have no terrestrial analogue. Solar wind implantation creates microscopic layers of altered material on particle surfaces. Cosmic ray bombardment generates distinctive isotopic signatures that record the duration and intensity of radiation exposure. Even the act of spiraling inward leaves its mark, as particles that have spent more time in the inner solar system show greater degrees of thermal processing than those recently arrived from the outer regions. Some of the most remarkable particles are those that have survived multiple passages through the asteroid belt, where the density of debris creates a kind of cosmic sandblasting environment. These grains bear the accumulated damage of countless microscopic impacts. their surfaces sculpted into complex topographies that record the violence of interplanetary space. Yet they continue their journey, testament to the remarkable durability of matter organized at the smallest scales of cosmic architecture. The concept of drift takes on profound meaning when applied to these cosmic snowflakes. Unlike terrestrial precipitation, which falls in response to gravity over timescales measured in minutes or hours, interplanetary dust drifts through space over timescales that encompass the rise and fall of entire species on Earth. A particle that began its earthward journey when the first complex life appeared in Earth's oceans might only now be approaching the final stages of its cosmic migration. Current observations suggest that approximately 40,000 of these particles settle onto each square kilometre of Earth's surface every day. This estimate, derived from satellite measurements, atmospheric sampling and analysis of terrestrial accumulation sites, carries with it uncertainties that reflect the fundamental challenge of measuring phenomena at such small scales across such vast distances. The actual flux likely varies with solar activity, planetary alignments, and the passage of Earth through different regions of the interplanetary debris field. The particles themselves display a remarkable diversity of composition and structure that reflects the heterogeneous nature of their origins. Some contain pristine materials that formed in the outer reaches of the solar nebula, preserving chemical and isotopic signatures from the earliest epochs of solar system history. Others show evidence of extensive thermal processing, the mineralogy altered by repeated exposure to solar radiation. A few contain organic compounds that formed through chemical processes in the cold vacuum of interstellar space. Molecular fossils from an era before the Sun existed. The study of these microscopic visitors requires techniques that push analytical chemistry to its absolute limits. Individual particles must be manipulated using focused ion beams and other nanoscale tools. Their chemical composition is determined using instruments capable of detecting individual atoms. Their crystal structure is revealed through electron diffraction patterns that require interpretation by specialists familiar with mineral phases that exist nowhere on Earth. Perhaps most remarkably, some of these particles contain presolar grains, microscopic diamonds, silicon carbide crystals, and other materials that condensed around stars that died before the Sun was born. These stellar fossils, embedded within the already microscopic dust grains like Russian nesting dolls made of cosmic matter, represent samples of the interstellar medium that existed billions of years ago. They carry within their crystal lattices the nuclear signatures of stellar nucleosynthesis, the element-building processes that occur in the cores of dying stars. The gentle drift of these cosmic snowflakes continues without pause, unaffected by human activity, climate change, or the passage of geological ages, right now. Particles that began their journey when the first animals crawled onto land are settling through Earth's upper atmosphere, their cosmic wandering finally approaching its end. Others, launched by comet outgassing events during the last ice age, still drift somewhere in the outer solar system, decades away from their eventual encounter with Earth's gravitational embrace. Only took a few million years for each grain to complete its migration from the outer darkness to Earth's welcoming atmosphere. And in that patient journey, each particle has become a messenger carrying news from regions of space that no human-made probe has ever visited. A microscopic time capsule preserving samples of cosmic processes that occurred long before observers evolved to wonder at their meaning. In the pristine expanses of Antarctica, where human footprints remain rare and the air carries no trace of industrial contamination, researchers have discovered one of the most extraordinary libraries ever assembled. This archive requires no shelves, no cataloguing system, no climate control beyond what nature provides. Instead, It exists as microscopic particles embedded within layers of ice that have accumulated over hundreds of thousands of years, each annual snowfall preserving a record of cosmic visitors that settled from space during Earth's slow journey around the Sun. The collection process began long before humans existed to recognize its significance. Each winter, as temperatures plunged and moisture crystallized from the thin Antarctic air, cosmic dust particles became incorporated into falling snow with the same gentle inevitability that captures pollen or volcanic ash. The particles settled onto the growing ice sheet, where they were buried by subsequent snowfalls and compressed into the glacial record. Layer by layer, season by season, the ice preserved samples of interplanetary material spanning geological ages. Modern ice core drilling operations, originally designed to study ancient climates, have inadvertently created the most comprehensive collection of extraterrestrial material available for scientific study. When researchers extract cylindrical cores from the Antarctic ice sheet, they recover not only trapped atmospheric gases and volcanic debris, but also microscopic samples of cosmic dust that fell during every year represented in the ice column. A single meter of ice core may contain thousands of these particles, each one preserved with the pristine clarity that only polar conditions can provide. The preservation is so complete that individual particles retain their original surface textures, chemical compositions, and even delicate structural features that would be destroyed by terrestrial weathering processes. Under scanning electron microscopes, these cosmic visitors display the same intricate surface topographies they possessed when they first entered Earth's atmosphere. Some show the characteristic signs of gentle atmospheric entry heating. Others reveal complex mineral assemblages that could only have formed in the exotic environments of interplanetary space. The Antarctic collection offers researchers something impossible to obtain through any other means: a time series record of cosmic dust flux spanning hundreds of millennia. By analyzing particles from different depths within ice cores, scientists can reconstruct how the rate of cosmic dust accumulation has varied throughout Earth's recent geological history. They can identify periods when comet impacts increased the dust flux, correlate particle chemistry with known meteor shower events, and trace the gradual evolution of interplanetary debris fields over time scales far longer than human observation. Some of the most remarkable discoveries have emerged from the deepest ice cores, where particles preserved for hundreds of thousands of years reveal compositions and structures that differ subtly from contemporary cosmic dust. These ancient samples suggest that the interplanetary environment has undergone slow but measurable changes as the solar system has evolved. The size distribution of particles, their chemical compositions, and their isotopic signatures all show variations that may reflect changes in comet activity, asteroid collision rates, or even the passage of the solar system through different regions of interstellar space. The process of extracting and analyzing these particles requires extraordinary patience and precision. Ice core sections must be melted in ultra-clean laboratory environments to prevent contamination from terrestrial dust. The resulting meltwater is filtered through systems capable of capturing particles just a few micrometers in diameter. Each filter is then examined grain by grain under high magnification microscopes, with promising candidates selected for detailed chemical and isotopic analysis. The isotopic signatures preserved in these particles provide windows into processes that occurred billions of years ago and trillions of kilometers away. Oxygen isotope ratios reveal the temperature and chemical conditions under which the particles first condensed from gas. Silicon and magnesium isotopes carry information about nuclear synthesis in the stellar cores where these elements were forged. Some particles contain isotopic anomalies so distinctive they can be traced to specific types of stellar environments. Red giant stars, supernovae, or the asymptotic giant branch stars where much of the galaxy's carbon was created. Perhaps most intriguingly, the Antarctic Archive preserves evidence of rare events that might otherwise go undetected. During years when large comets made close approaches to the Sun, the cosmic dust flux increased dramatically as these ancient visitors shed vast quantities of material. The ice cores record these events as spikes in extraterrestrial particle concentration, creating a record of comet activity that extends far beyond the brief span of human astronomical observation. The organic chemistry preserved in these particles tells stories of molecular evolution in environments utterly unlike anything found on Earth. Complex carbon compounds, formed through reactions in the cold vacuum of interstellar space, remain stable within the ice matrix for geological ages. These molecular fossils include polycyclic aromatic hydrocarbons, amino acid precursors, and other compounds that may have played crucial roles in the chemical evolution that eventually led to life on Earth. Some particles recovered from Antarctic ice show signs of having originated beyond the solar system entirely. These interstellar visitors, captured during the solar system's passage through dense regions of the interstellar medium, carry chemical and isotopic signatures that differ markedly from locally produced cosmic dust. Their presence in the ice record provides direct samples of the matter that fills the space between stars, material that forms the raw material from which future solar systems will eventually condense. The seasonal variations preserved in the ice reveal the subtle rhythms of cosmic dust accumulation throughout the year. During certain months, when Earth's orbital motion carries it through regions of higher debris density, particle concentrations in the ice increase measurably. These seasonal patterns, repeated year after year in the glacial record, provide confirmation of the organized structure within the interplanetary dust cloud and demonstrate how Earth's changing position relative to this debris field affects the rate of extraterrestrial material accumulation. Recent advances in analytical techniques have enabled researchers to perform increasingly sophisticated analyses on ever smaller samples. Individual particles weighing less than a picogram can now be analyzed for their complete chemical composition, crystal structure, and isotopic signatures. These capabilities have revealed that even particles that appear similar under optical microscopy often display remarkable diversity in their detailed properties, reflecting the complex and varied processes that shape them during their cosmic journeys. The mystery of seasonal variations in particle chemistry adds another layer of complexity to the Antarctic Archive. Cosmic dust that arrives during different times a year shows subtle but measurable differences in composition and structure, suggesting that Earth encounters debris streams with distinct origins and evolutionary histories as it follows its orbital path around the Sun. These compositional variations provide clues about the three-dimensional structure of the interplanetary dust cloud and the processes that organize debris into streams and clusters. The Antarctic collection continues to grow with each passing season, as fresh snowfall incorporates contemporary cosmic dust into the ongoing glacial record. Current accumulation rates suggest that future researchers will eventually have access to ice core samples spanning millions of years, creating an unparalleled archive of solar system evolution preserved in crystalline clarity. The particles falling today will join their predecessors in the polar ice, adding new chapters to a story written in microscopic detail across the vast scales of cosmic time. In the pristine silence of the Antarctic interior, where the only sounds are the whisper of wind across ice and the distant crack of shifting glaciers, this cosmic library grows grain by grain, breath by breath, preserving samples of infinity and the patient accumulation of polar snow. Only took a few 100,000 years to build an archive of the universe written in ice and starlight, and the collection continues. adding its microscopic treasures to the frozen memory of a planet that has been gathering evidence of its cosmic neighborhood since the ice began to fall. The Moon maintains its own silent archive of cosmic dust accumulation, a library written not in ice but in the airless vacuum that has preserved samples of interplanetary material for billions of years. Unlike Earth, where atmospheric weathering and geological processes continuously erase evidence of cosmic bombardment, the lunar surface offers a nearly perfect preservation environment where particles that settled during the earliest epochs of solar system history remain essentially unchanged, embedded in the regolith like fossils frozen in time. When the Apollo astronauts returned from their expeditions carrying sealed containers of lunar soil, they unknowingly brought back some of the most comprehensive samples of ancient cosmic dust ever collected. The grey powder that clung to their spacesuits and equipment contained not only pulverized lunar bedrock, but also countless microscopic particles that had drifted through interplanetary space for millions of years before settling onto the Moon's unprotected surface. Each handful of lunar regolith represents a mixture of local and extraterrestrial materials, a cosmic sediment that has been accumulating without interruption since the Moon's formation. The preservation conditions on the lunar surface approach the ideal for maintaining cosmic dust in its original state. With no atmosphere to create oxidizing conditions, no water to drive chemical reactions, and no biological activity to contaminate samples, particles that land on the Moon remain essentially unchanged for geological ages. Temperature variations between lunar day and night do subject the material to thermal cycling, but without the presence of moisture or reactive gases, these temperature swings cause minimal alteration to the particle's fundamental properties. Laboratory analysis of lunar soil samples has revealed that between 1 and 2% of the regolith consists of extraterrestrial material, cosmic dust particles that accumulated over the Moon's 4 billion year history. This percentage may seem small, but it represents an enormous quantity of interplanetary material when distributed across the Moon's entire surface. Scientists estimate that the upper layers of lunar regolith contain somewhere between 10 to the 11th and 10 to the 12th kilograms of cosmic dust, making the Moon's surface one of the largest accessible repositories of extraterrestrial matter in the inner solar system. The isotopic signatures preserved in these particles provide unprecedented insights into the evolution of the interplanetary dust environment over geological time, unlike terrestrial samples, which represent only the most recent accumulation. Lunar soil contains particles that settled billions of years ago when the solar system was young and the interplanetary environment was dramatically different from its current state. Heavy bombardment periods, ancient comet impacts, and the gradual evolution of asteroid belt dynamics are all recorded in the microscopic debris embedded within lunar regolith. Some of the most remarkable discoveries have come from the analysis of individual particles extracted from Apollo soil samples. These microscopic grains, painstakingly separated from the lunar matrix using techniques that can isolate objects smaller than bacteria, display compositions and structures that reveal their extraterrestrial origins with unmistakable clarity. Many contain mineral assemblages that could not have formed under lunar conditions, isotopic ratios that differ markedly from solar system norms, and organic compounds that bear the chemical signatures of interstellar space. The lunar regolith acts as a kind of natural mass spectrometer, concentrating and preserving samples of cosmic dust that would be difficult or impossible to study through any other means. The absence of atmospheric entry heating means that even the most delicate particles arrive at the lunar surface in pristine condition, their original textures and chemical compositions intact. Volatile compounds that would be lost during passage through Earth's atmosphere remain preserved in lunar samples, providing insights into the chemistry of interplanetary space that cannot be obtained from terrestrial collections. Recent reanalysis of archived Apollo samples using modern analytical techniques has revealed details that were invisible to earlier generations of instruments. Secondary ion mass spectrometry, capable of detecting trace elements at concentrations measured in parts per billion, has identified exotic isotopic signatures that point to stellar environments where these particles originally formed. Transmission electron microscopy reveals crystal structures and mineral phases that provide clues about the physical conditions these grains experienced during their cosmic journeys. The distribution of cosmic dust within lunar soil samples provides information about accumulation rates and flux variations over geological time. By analyzing samples from different Apollo landing sites and different depths within the regolith, researchers can reconstruct how the cosmic dust environment has evolved as the solar system has aged. The data suggests that accumulation rates have varied significantly throughout lunar history, with periods of enhanced bombardment corresponding to major disruptions in the asteroid belt and increased comet activity. Some particles in lunar soil display evidence of multiple cosmic ray exposure events, suggesting complex histories that involved ejection from their parent bodies, long periods of interplanetary travel, and eventual capture by the Earth-Moon system. These multiply exposed grains carry within their crystal lattices the accumulated damage from billions of years of cosmic radiation, creating microscopic records of radiation environments in different regions of the solar system and different epochs of solar system evolution. The lunar samples also preserve evidence of the early solar system's violent history in ways that terrestrial samples cannot. During the late heavy bombardment, approximately 4 billion years ago, when asteroids and comets pummeled the inner planets with unprecedented intensity, the Moon's surface was resurfaced by impact events that mixed deep crustal material with contemporary cosmic dust. The resulting breccias contain fragments of very ancient cosmic dust embedded within impact melt rocks, preserving samples of the interplanetary environment from the earliest phases of planetary evolution. Advanced analytical techniques have revealed that some particles in lunar regolith contain presolar grains, microscopic diamonds, silicon carbide crystals, and other materials that condensed around stars that existed before the Sun formed. These stellar fossils, embedded within cosmic dust particles that are themselves embedded within lunar soil, represent samples of the interstellar medium that existed billions of years ago. They carry isotopic signatures of nucleosynthesis processes that occurred in stellar cores that completed their evolution before the solar nebula began to collapse. The organic chemistry preserved in lunar cosmic dust particles tells stories of molecular evolution in environments completely isolated from biological processes. Complex carbon compounds formed through purely chemical reactions in the vacuum of space remain stable within lunar samples for geological ages. These molecular fossils include compounds that may have served as precursors to the chemistry that eventually led to life on Earth. Preserved in lunar samples with clarity that cannot be achieved in terrestrial environments. The absence of atmospheric shielding means that the Moon continues to accumulate cosmic dust at rates that can be measured and studied in real time. Current estimates suggest that approximately 10 to the minus 15 grams of cosmic dust settle onto each square centimetre of lunar surface every year, a rate so low that it would take millions of years to accumulate a layer thick enough to be visible to the naked eye, yet significant enough to continuously add new samples to the lunar archive. Future lunar missions will likely focus on systematic sampling of regolith from different regions and depths, creating a comprehensive map of cosmic dust distribution across the Moon's surface and throughout its geological history. The lunar far side, permanently shielded from Earth's gravitational influence and magnetic field, may preserve cosmic dust samples with compositions and structures that differ from those found in near-side regolith. The polar regions, where permanently shadowed craters have collected material for billions of years, represent another frontier for cosmic dust research. The Moon's role as a natural collector and preserver of cosmic dust makes it an invaluable resource for understanding the history and evolution of the interplanetary environment. Unlike any terrestrial archive, the lunar regolith preserves samples spanning the entire history of the solar system, from the earliest epochs of planetary formation to the present day. Each grain of lunar soil contains within it microscopic samples of cosmic dust that tell stories of stellar evolution, interplanetary dynamics, and the slow chemical evolution of the space between worlds in the vacuum silence of the lunar surface, where no wind disturbs the ancient dust and no weather erases the records of cosmic bombardment. This microscopic archive continues to grow particle by particle, preserving evidence of the universe's ongoing evolution in a museum without walls or atmosphere. The grey powder that future astronauts will find beneath their boots represents billions of years of patient accumulation, each microscopic grain a page in the longest book ever written, a story told in the language of atoms and starlight across the immeasurable distances between worlds. Only took 4 billion years to build a library made of vacuum and cosmic debris, and still the collection grows, adding its ancient treasures to the airless memory of a world that has been gathering evidence of cosmic history since the solar system learned to dream in stone and shadow.